Today we are going to discuss about binary search. Binary search follows divide and conquer method. We have already discussed about divide and conquer method. In divide and conquer method, a big problem is divided into a number of sub-problems and these sub-problems are solved recursively. Binary search algorithm has a prerequisite. It requires that the list that has to be searched should be in a sorted order, either in ascending order or in descending order. Now let us see an example. Now take an example. Suppose this is the list that has to be searched. As we have already discussed, the list should be in the sorted order. Suppose the key element that has to be searched is 7. We'll write the index. The index starts from 0 to 7. We'll take two variables, low and high. Low is the starting index and high is the ending index. We have to find out the mid element. Mid element is given by low plus high divided by 2. Basing on this mid element, we will divide the list into two sublists. Now low is 0 and high is 7. Mid is calculated as low plus high divided by 2. We will take the floor value. Now 7 by 2 is 3.5. We will take the floor value, that is 3. Now A of mid is A of 3. A of 3 is nothing but 9. So basing on this mid element, we will divide the list into two sublists. One is left sublist and one is right sublist. Now we will come across three subcases. One is key is equal to A of mid. When key is equal to A of mid, it means that the search is successful. Second case, when key is less than A of mid. When key is less than A of mid, we will search the left sublist. That means the search element or the search key is found in the left sublist. And the third case is key is greater than A of mid. When key is greater than A of mid, we will search the right sublist. That means the search key element will be found in the right sublist. Okay, now let us observe all these cases. Now let us come to our example. A of mid is A of 3, that is 9, and the key element that has to be searched is 7. We have to check all these cases. Is key is equal to A of mid? No, key is not equal to A of mid. Is key less than A of mid? Yes, key is less than A of mid. So we have to search the left sublist. Okay, let's draw the list again. 3, 5, 7, 9, 11, 16, 18 and 25. Okay, the 9 is the mid. Left sublist has 3, 5, 7. Right sublist has 11, 16, 18 and 25. Key is less than A of mid, so we have to search the left sublist. This is the left sublist. 0, 1, 2. So low is 0, high is 2. We have to calculate the mid for this sublist. Okay, again mid is given by low plus high divided by 2, that is 1. A of mid is equal to A of 1, that is 5. Again we have to check this A of mid element with the key element. Now the list is divided like this. Is key is equal to A of mid? Is key is equal to A of mid? No, key is not equal to A of mid. Is key less than A of mid? No, key is not less than A of mid. Is key greater than A of mid? Yes, key is greater than A of mid. So we have to search the right sublist. So this is the right sublist. For the right sublist we have to calculate the mid. Okay, now for the right sublist, low is equal to 2, high is equal to 2, and mid is given by low plus high divided by 2. Now A of mid is equal to A of 2, that is equal to 7. Now let's check. Is key is equal to A of mid? Yes, key is equal to A of mid. Search is successful. What we have done, we have taken the entire sublist, we have found the mid element, and basing on that mid element we have divided the list into two sublists, left sublist and right sublist. Basing on the mid value only, we have to select whether we have to search the left sublist or we have to search the right sublist. After finding the left sublist or right sublist, we have to again apply the same procedure, find out the mid and apply the process recursively. This is how the search is going to happen. Now let us take another example in which we'll see that the search is unsuccessful. Okay, let's take key is equal to 10. Let's draw the list again. Three, 5, 7, 9, 11, 16, 18 and 25. Okay, 0, 1, 2, 3, 4, 5, 6, 7. Low is 0 and high is 7. We have to find out the mid element. Mid is given by low plus high by 2, that is 3. Okay, now let's check A of mid value with the key value. A of mid is 9 and the key value is 10. We have to compare this mid value with the key value. The right sublist has 11, 16, 18 and 25. The index is 4, 5, 6, 7. Okay, now we have divided the list into two sublists, left sublist and right sublist, and the mid element is 9 and the key value is 10. Now let us check the three cases. The first case is key equal to A of mid. Key is not equal to A of mid. Is key less than A of mid? No. Is key greater than A of mid? Yes, key is greater than A of mid. So we have to search the right sublist. Okay. For how long shall we divide the list? There is a stopping condition for the division also. That is while low is less than or equal to high. While low is less than or equal to high, we have to divide the list. Now coming to this right sublist, we have to calculate the mid element. Mid element is calculated by low plus high divided by 2. Now low is 4 and high is 7. Okay. Here low is less than or equal to high. Okay, we will divide the list. Mid is given by low plus high divided by 2. 4 plus 7 divided by 2, that is 11 by 2. We take the floor value, so answer is 5. A of mid is given by A of 5, that is 16. Now compare this A of mid with key value. Key is 10. A of mid is 16, key is 10. So key is less than A of mid. That means we have to search the left sublist. Now here is the list: 11, 16, 18, 25 and 16 is the mid, and left sublist has 11, right sublist has 18 and 25. Left sublist index is 4 and this is 6 and 7. 16 is the mid. Okay, now we have to search the left sublist as key is less than A of mid. This is the left sublist. For the left sublist, low is 4. high is 4 and mid is given by low plus high divided by 2. That is 4 plus 4 by 2. That is 4. Now let's check, is A of mid equal to key? A of 4, that is equal to 11. Is A of mid equal to key? No. Is key greater than A of mid? No. Is key less than A of mid? Yes. Key is less than A of mid. So we have to search the left sublist, that is this list. Okay. For the left sublist, again we have to calculate the values of low and high. If the list is divided into left sublist, what are the values? Low is going to be low only, but high is going to be mid minus 1. So low is equal to low only. Low only, the previous value of low is 4. Okay, so the value of low is 4 only, but the high is equal to mid minus 1. So here low is equal to 4 and high is equal to mid minus 1, that is 4 minus 1, that is equal to 3. Now low is greater than high, but our condition is low should be less than or equal to high. Here low is greater than high. That means we cannot divide the list further. That means we have come to an end of our search. Search is unsuccessful. This is how binary search happens in a list. Now let us see the algorithm for binary search. Binary search accepts the inputs array with n elements and key element. A is the array and the size of the array is n. Let us take low is equal to 1 and high is equal to n. While low is less than or equal to high, find mid. Mid is equal to low plus high divided by 2. We have to compare this mid element with the key element. Okay, if key is less than A of mid, we have to search the left sublist. Then low will become low only, but high will become mid minus 1. Then high is equal to mid minus 1. If key is greater than A of mid, we have to search the right sublist. Then high will remain the same, but low will become mid plus 1. Else, that means key is not less than A of mid, key is not greater than A of mid. It means key is equal to A of mid. Else return mid. This is while low less than or equal to high. If low becomes greater than high, that means the search is unsuccessful. We have to return 0. So this is the algorithm for binary search. So this is the list, and basing on the mid element, we are dividing the list into left sublist and right sublist. This is low and this is high. For the left sublist, low will become low only, but high will become mid minus 1. For the right sublist, high will be high only, but the low will become mid plus 1. Okay, so this loop will be continued until low is less than or equal to high. When low becomes greater than high, it returns 0. That means search is unsuccessful. Okay. Now coming to the time complexity of binary search. For the time complexity, we have to analyze three cases: best case, worst case, and average case. What is the best case? The best case is the case where we have the middle element as the key element. That means we have found out the middle element and the middle element is equal to key element. The number of comparisons we have done is only 1, and the time complexity is order of 1. This is because we have done only one comparison. This is the best case time complexity. Binary means 2. What we have done in this binary search, we have taken the list and we have divided the list into 2 sublists. What we have done, we have made the search space into half. We have divided the total list into 2 lists. For average case and worst case, basing on the mid element, we have divided the list into 2 sublists. That means the total time taken is reduced to half. So T of n is equal to T of n by 2 plus 1. What is this one? This one is used for division and for comparison. Okay. Division and comparison. Now let us expand this T of n by 2. Again T of n by 2 can be written as T of n by 4 plus 1 plus 1. As T of n by 2 is equal to T of n by 4 plus 1. Okay, T of n by 4 can be written as T of n by 8 plus 1 plus 1 plus 1. That is written as T of n by 2 cube plus 3. Like this we can write as T of n by 2 power k plus k. Okay, now let us assume that 2 power k is equal to n. That means the total list, let us assume that the list of elements is in the power of 2 or multiples of 2. The list is in the order of 2. Let us assume that 2 power k is equal to n. It means the list of elements that has to be searched is in the order of 2, multiples of 2. Okay, so 2 power k is equal to n, applying logarithm on both sides. Log 2 power k is equal to log n. That is k log 2 is equal to log n. Log 2 base 2 is 1. Therefore k is equal to log n. Applying this in the previous equation, we have T of n by n plus log n. T of n by n is T of 1, that is 1 plus log n. That is log n. Therefore, time complexity is order of log n. So, this is the time complexity for binary search.